Math 8, Unit 8, Lesson 4. Linear models of bivariate data. We'll be going over the scatter diagram lab the week after spring break when we start talking about lines of best fit. Today we're just talking about lines of fit. Lines of best fit would be using a computer. Well, actually it's a mathematical algorithm, but a computer is really good at doing it to find the best line. Okay, how to create a linear model. First, you're going to draw a line of fit and you pick 2 points. And for example, here on this evening newspapers, I picked the point -4, 850 and the point 2, 700. So first step, draw a line and pick 2 points that it goes through. Now these points do not have to be data points. They just need to be points on the line. It's nice if you use data points, but doesn't necessarily have to be. Next, you're going to use the 2 points to write an equation. Remember the steps there. You first find the slope. You do your subtraction fraction. This is 850 minus 700, the y's subtracted. And then on bottom, -4 minus 2, the x is subtracted. You reduce that down, we get a slope of -25. And then you do your y equals mx plus b. You plug in a point. I plugged in 2, 700. You solve down for b. And then you get your equation, y equals -25x plus 750 in this situation. Then you use the linear model as needed to answer questions. So, for example, use the model to estimate the number of evening newspapers in 2010. Well, in 2010, x is going to equal 10. So, we plug in 10 for x, -25 times 10 plus 750, we get 500. There are 500 evening newspapers in 2010, according to this linear model. And the rate could have changed. The linear model here works very well between the years of 1995 and 2003. It may not work so well by 2010, but it might. We'd have to compare it to the actual data to know. There are some other things you'd be asked to interpret here. You may be asked to interpret the meaning of the slope. Now, slope is change in y over change in x, change in the number of newspapers over the change in years. So this -25 would mean the evening newspapers tends to decrease by 25 each year. Tends to. It doesn't exactly decrease by 25, but it tends to decrease by 25. The y-intercept here of 750, you need to consider what does it mean for x to equal 0. Well, in this case, x equaling 0 is the year 2000. So 750 newspapers, there were 750 newspapers in the year 2000. Okay, write a linear model function to model the calories burned during exercise. Alright, on this one, I don't have any quick click and it shows up type thing. I'm just doing this one from scratch. You first draw a line that tends to go through the points fairly well. Let me see my line. I've got some points below it, some points above it. It looks like it tends to follow it, so we're going to go with that. It looks pretty good. Let's use this point that looks like it's about 1075. And what's another good point we could use? This one's not on the line, but let's go ahead and use it. It'd be about 55,500. Okay, so we're going to need to find the slope here. Let's do 500 minus 75 on top and 55 minus 10 on bottom. I'm going to grab my trusty calculator. Let's see, this is 425 on top and 45 on bottom. 425 divided by 45 is, I'm just going to go with the decimal here, 9.444. I'm just going to go 9.4. Okay, so that is my slope. Remember from there, We could almost estimate what the y-intercept is here. We can't quite see it. It's probably around -20, -25. But just going to find out for sure. We're going to do y equals 9.4x plus b. And we're going to plug in for y and for x and then solve. Let's do this 1075. So 75 for y. Whoops, pressed the wrong button there. 75 equals 9.4 times 10 plus b. 9.4 times 10 is 94, so we're going to subtract 94 from both sides. And 75 minus 94 is -19. I said it looked like about -20, -25, so that's a pretty good estimate. So the linear function to model the calories burned during exercise, we could do just y equals 9.4x minus 19, and it could be done as a function in function notation. The calories given the number of minutes is 9.4 times the number of minutes minus 19, according to this linear model. Now either of those forms would work here. Use the model to predict the number of calories burned in 1.5 hours. Now 1.5 hours is going to be a time equal to 90 minutes. We do have to convert that because our input is in minutes. So we're going to plug in 90 minutes. This is going to be 9.4 times 90 minutes minus 19. 9.4 times 90 minutes minus 19, and that gives us 827 calories. Okay, use the model to predict the number of minutes needed to burn 1,000 calories. All right, 1,000 calories. Calories are on my y-axis, so I will plug in 1,000 for my y, my output. And I'm just going to copy down the functions from above with 1,000 plugged in for y. Let's go ahead and add the 19 to both sides. This is 1019 equals 9.4x. We'll go ahead and divide, and we should have x by itself now. According to this, it came out 108.4, so about 108 minutes. Getting up pretty close to 2 hours by that point. Okay, next example. The table shows the number of people who have attended a festival over an 8-year period. A. Make a scatter plot of the data and draw the line of fit. B. Write an equation of the line of fit. C. Interpret the slope and y-intercept of the line of fit. And D. Predict the number of people who will attend the festival in year 10. Okay. So first, just to save time, I've plotted these points previously. Notice that I have labeled the x-axis with year and the y-axis with attendance, which I got right here out of the table. Not really too complicated there. And then I took every one of these ordered pairs, 1, 420, and plotted it. 2, 500 and plotted it. So those are all plotted. That's it for part A. Part B, write an equation of the line of fit. Oh wait, part A, I still need to draw the line. Let me see what I can come up with here. Let me modify that a little. That's looking pretty good. Yeah, I like that. It looks all right. So there's a little bit of guesswork involved here unless you use the mathematical method, usually just done with a computer now, to find the line of best fit. But we'll just go with this one. Write an equation of the line. Okay, this line goes through a couple of points. I kind of specifically chose this point 0, 0. And if we look through here, it looks like it goes nicely through right here at 7, 1800. So we're going to use that one as well. Okay, so the slope is going to be 1800 minus 0 over 7 minus 0. That's 1800 over 7. That's not going to be a nice whole number. I get 257.1428. So 257.1. In fact, I'm just going to make it 257, round to the nearest whole number. Because 257, rounded to the nearest whole number, if you look at our numbers 1, 2, 3, or 200, 400, 600, 800, it's going to be pretty accurate even going to the nearest whole number. So y is 257x plus b. Now pick one of our numbers. Let's actually just do 500. That one looks easy to use. So this is 500 equals 257 times 2 plus b. 257 times 2 is 514. Wait, I need to back up a second here. I need to use one of the points that are on my line, not one of the points out of the data set. So over here on my line, I do have the point 0, 0, which makes a lot of good sense to use because then we just find out that b equals 0, which is very nice. So y is 257x for our equation. All right, part C, interpret the slope and the y-intercept. All right, our slope here is 257. Now 257, we need to look, it's y per x, that's attendance, number of people, per x, year, people per year. So the attendance tends to increase by 257 people per year. Okay, so attendance is increasing over time. Very nice. The y-intercept. The y-intercept here is 0. And what it would mean, in year 0 there were 0 people, which I guess kind of makes sense, but I want you to think for a moment. There was no festival in year 0. It didn't start until year 1. That was the first festival, and then year 2 was the second festival. So this y-intercept, yes, it is true that in year 0 there were 0 people attending, but talking about the 0th year of a festival actually doesn't have real-world meaning. This is just a mathematical construct to make the numbers work out. But with that having been said, we're just going to go the in year 0, 0 people attended. But it's important to understand what I just meant about in year 0. It doesn't have real world sense here, but it does make the mathematical model work. Part D, predict the number of people who will attend the festival in year 10. Okay, for year 10, x equals 10. Okay, x is the year. So we're just going to take y equals 257, multiply it by 10. We get 2,570 people, and this is the number of people we would expect to show up in year 10. Next example. The scatter plot shows the weight y of an infant from birth through x months. At what age did the infant weigh 11 pounds? Okay, let's just look at this. 11 pounds. Looks like 3 months. It's right there on the graph. It's one of the points. Very nice. What was the infant's weight at birth? Okay, birth would be at 0 months. So we go and look at 0 months, and it looks like the infant was 7 pounds. 7 pounds at birth. That's a common birth weight. There were probably some ounces in there, 7 pounds, 2 ounces, something like that. Draw a line that you think best approximates the points. Okay, doing a line here. Ooh, that looks pretty good. Now, I did on this one use the y-intercept of the birth weight, and I tried to make it as close to the points as possible. So that looks really good. And that is done now. Write an equation for your line. All right. I'm going to have to do the work on that down here towards the bottom. We've got 2 points here that we probably should use, 0, 7, and I like the looks of that 12, 22. So let's use 0, 7 and 12, 22. I went a little too far down. Okay, first, the slope. Let's do 22 minus 7 over 12 minus 0. 22 minus 7 is 15 over 12. Well, this is going to work out pretty nice. 15 over 12 is 1.25. Okay, so y equals 1.25, x plus b. And actually we know b because we had one of our points be the y-intercept. So we have our equation. And we'll just drag it back up into here, if I can get it to fit all right. It's kind of a little on the big side. Okay, so our equation for the line of fit, y equals 1.25x plus 7. Use the equation to predict the weight of an infant at 18 months. Okay, since months is on the x-axis, I will plug in x equals 18. So y is 1.25 times 18 plus 7. 1.25 times 18 plus 7. And I get 29.5 pounds. So a 1.5-year-old you would expect to be around 30 pounds. Does the data show a positive, a negative, or no relationship? This is definitely a positive relationship. As an infant gets older, they tend to weigh more. That's kind of how growing works. Is your linear model reasonable for a 13-year-old? All right, let's think about whether this would work for a 13-year-old. What would be the age in months for a 13-year-old? Well, that's 12 months times 13. So on their 13th birthday, they would be 156 months old. So a 13-year-old on their birthday is 156 months old. Let's see if this makes sense in this model. Let's plug in 156 months and see what we come up with. 1.25 times 156 plus 7 gives us a weight of 202 pounds. Now let's think about this, whether that's reasonable or not. Are there 13-year-olds that weigh 202 pounds? Yes. Is it a common weight for a 13-year-old? I don't think so on that one. That's kind of hitting the upper end of weight. The average 13-year-old probably weighs between 110 and 150, 170 maybe, depending on how much muscle they've developed. And so that is a bit high. So is it reasonable? Maybe. For some people it might be, depending on their genetics and bone structure. But I'm going to go with maybe, but not for your average 13-year-old. Now let's think about another reason why this might not work very well for a 13-year-old. In fact, if we figured it out for a 35-year-old, we'd probably have some big problems because humans don't grow at the same rate throughout their whole life as they did when they were infants. In fact, let's look at a 35-year-old. A 35-year-old on their 35th birthday is 420 months old. If we do 1.25 times 420 months plus 7, we would expect a 35-year-old to be 532 pounds. Now, are there 35-year-olds that weigh 532 pounds? Yeah, there are. But it's not the average. The average 35-year-old probably weighs, well, depending on if male or female. Yeah, that does make a difference. The average adult male 35-year-old is going to be somewhere between 180 and 240 pounds. I mean, there's kind of a wide range. And there's, of course, ones outside of that range. But 532 pounds would be very, very big. So not very good model there. Okay, in your assignment, on number 1, you're going to draw a line of fit and write an equation. Now for this one, where there's no relationship, you'll just say no relationship, so you won't need to write an equation on that one. Number 2, you're going to draw a line of fit, find the slope, write a prediction equation, and then on part D and E, you're going to use it to make predictions. 3, 4, 5, and 6 are your review problems. Looks like 3, you get to solve a 2-step equation. Number 4, you're going to plug in 17 into the g of x function. Number 5, you're going to find the third angle in a triangle. Remember, triangles, angles add up to 180. Number 6, you find the distance. Remember the distance formula from unit 6. Number 7, on this one, you're going to plot some points. This is looking at bat populations. And you're going to graph the data, draw a line, make a prediction equation, interpret the meaning of the slope, and then y-intercept. On number 8, it's about the same data from number 7. You're going to predict the number of bats at some different years, and you're going to predict the number of bat when it'll be less than 10,000, and then do you think this is valid for the 20-year out from now, or for 20 years from the beginning. Please complete your assignment. When you're done with it, make sure to correct it with the correction video and upload it to Canvas. Thank you for watching.